I will talk today about adaptive digital fabrication, and will show you some thoughts and some examples of my work on adaptive digital fabrication. A bit of my background, Danielle already introduced me. My name is Daniela Mitterberger, a postdoc at Grammatio Cola Research and co-lead of the Immersive Design Lab that you can see behind me at Design++. And in my work, I deal with two realities: the physical built environment in which humans interact, and the digital design environment. And the lab that you can see behind me focuses exactly on this question, on how we can immerse human body and humans in the digital realm, and how we can combine these two realities back together. Besides co-leading the Immersive Design Lab that I just showed you, my work is also following this line of thought on how to track human actions and include human decision-making in digital processes. I'm by that redefining the role of the human in digital design and robotic fabrication. We saw already a little bit on why this is important, and I will just say a little bit about it, why I do the work that I do. Until now, most digital processes strongly separate these two realities, aiming for very feed-forward processes. So these processes are based on well-defined linear sequences of actions, where the work environment, materials, and processes are constant. And of course, this brings limitations. So if we look at the construction site and the construction industry, we find a lot of processes that are unpredictable, inaccurate, complex, or involve materials with nonlinear behavior, such as mortar. And it is these characteristics that make these processes very difficult to automate, and why most of them still rely on manual labor. Humans are able to react very quickly, and we can improvise to complex situations due to our tacit knowledge and context awareness. We're also very texturous. That means we can work very well with malleable and soft materials. This is also the reasons why we are still necessary to assist with the shortcomings of robotic fabrication and digital fabrication. We saw this picture yesterday already with Stefana's presentation, and we see, and we talked about it, that our role in digital fabrication is still very marginalized. And the reason for that is that our actions are not really included in the digital control logic. And this is exactly where my research is adding on to. So I focus on adaptive digital fabrication processes and human-machine collaboration architecture, asking how we can include human actions and decisions better in digital design and robotic fabrication. For this, I look on how to augment humans with extended reality interfaces, how to use tracking systems to track the actions and positions of humans, and which feedback-based computational models are needed to synchronize the digital with the physical workspace. And depending on who is fabricating, the human, the machine, or both together, different human-machine feedback loops are required to enable cooperative building. So this inclusion of humans extends also the possibilities of digital fabrication and enables various possible scenarios, such as digital craft, interactive and collaborative fabrication, and embodied computation. And I want to show 4 projects today, very briefly, to introduce all of these concepts, to show the potential that we have if we actually push towards more adaptive digital fabrication projects. An example of what I understand as digital craft is augmented bricklaying, a project actually done together with Professor Katrin Dörfler when she was still at Grammatio Cola Research at ETH. And it explores the craft of bricklaying and how masons can be instructed in real time by an augmented reality system and a visual inertial object tracking system, where we collaborated with Dr. Timothy Sandy and Incon. And augmented bricklaying asks the questions on how we can enable humans to build more complex structures with robotic precision while preserving craft qualities. And the research started with the questions on how we can fabricate complex and digital-informed brickwork nowadays with the new technologies that we have. And we found 3 methods. The first one, manual fabrication with dependencies on physical templates. The second one, robotic fabrication with limitations for on-site use and materials such as mortar. And the third one, augmented fabrication, combining human dexterity with geometric precision of machines. To build with augmented fabrication, I needed to be able to inform humans on where and how to assemble brick walls. For this, I tracked the position of bricks in space using the visual inertial object tracking algorithm of Timothy Sandy and combined it with current CAD models and a craft-specific user interface. One key point of this research was the development of this craft-specific user interface, informing masons on how to assemble brick walls. Masons, if we talk with them, already have a technique to adjust bricks in space. So they tap on them with their trowels to make very fine, precise adjustments. And in the visual interface, I included this craft-specific knowledge and used arrows to show masons in real time on how strong and where to tap the bricks. The length of the arrow indicated the strength of the tap, and the position informed them about the location of the tap. One advantage of using augmented fabrication is that we can use extensive amounts of mortar, something that is unthinkable for brick assembly with robots, or very hard to achieve. And the building project in Keynotes, where we built the whole facade, and until now, currently the largest ever built facade and building using augmented reality, allowed us to test the whole workflow and system over a period of 8 months and under outdoor conditions. After 3 months, we finished the facade, proving that such a system eliminates the need for bricklayers to rely on physical templates to build digitally informed brickworks, while still utilizing their expertise in handling mortar, thus both preserving and enhancing their craft. The next project that I would like to show moves on the other side of the spectrum. It focuses on interactive fabrication, also a different type of digital craft, with not the human as an actuator, the human that is building, but actually the machine that is building and the human that gives the input. It is called interactive robotic plastering. It was done in collaboration with Selen Erkan Jenny, and combined an augmented interactive design and fabrication system with a robotic plastering process. It was the first time that a plastering process was paired with an interactive fabrication setup. And IROB aimed to discover the technological and aesthetical potentials of combining human intuition and creativity with robotic fabrication, and asks how we can enable humans to engage intuitively with an in-situ robotic plastering process. The research combined 3 parts: an interactive design setup, an augmented reality setup, and a robotic plastering setup. It utilized a controller-based interaction system to enable humans to interactively design and fabricate articulated plasterwork in situ, taking the building structure and the as-built state of the construction site into consideration. The design workflow of IROB allowed humans to generate complex digital models in minutes and rapidly generate multiple design alternatives. It further allowed humans also to, with very limited programming skills, to instruct a robot by demonstration. With the software of IROB, humans could define an aesthetic style of the plasterwork, and that meant that they did not choose a predetermined geometry to spray plaster, but actually pick a translation style from human to machine. These styles allowed humans to translate and remap their analog human input, such as hand movements, into robotic output. And the purpose of this style system was to allow creativity while still ensuring that whatever the humans are designing interactively on a construction site still complies with material and machine constraints. An example of such a style is, I call it the carving effect. It translates hand distance to a wall in 3D to end effector distance to a surface. And this resulted in ripples on the sprayed plaster. So the reason for this was the closer the end effector was to the surface, the more liquid plaster got pushed away from the air coming from the spray nozzle. So by using this filter, humans were able to creatively and intuitively adjust the texture of the wall, and here you can see some examples. To test the workflow, we were building a full-scale architectural prototype where everything, the design and the fabrication, happened entirely on site. And this structure demonstrated how IROB can be used to design and fabricate novel forms of 3-dimensional plasterwork. But the aim was also to develop an entirely new way of designing and design thinking, a new interactive fabrication and digital craft that combined computational logic with tacit human knowledge and intuition. Moving from the human as the fabricator to the machine as the fabricator, we look now what happens if we both work together through hybrid human-robot cooperation. And I especially picked that project here because if you join the workshop, you will also get hands-on experience with us working on this project. Tayanot investigated what is necessary for humans to assemble structures cooperatively with robots. It was a project done in collaboration with TU Munich, with Lidia Atanasova and Katrin Dörfler, and it was, the goal was to develop workflows to combine manual and machine assembly for complex wooden structures using rope joints. And in Tayanot, humans and robots were aiming to build complex structures cooperatively. So that means that manually placed elements did not disrupt the digital workflow, but were integrated into a digital twin and result in follow-up robotic actions. And to enable such a cooperative assembly workflow, we developed a system that consisted of 5 turn-taking tasks between 2 humans and 2 robots. So that meant that humans were able to initiate design and assembly cycles that then were continued, assisted, and completed by the cooperating robots. The assembly cycles were linked to the smallest units of the structure. We call it the Y triplets, and these Y triplets were made of 3 struts, one from a previous element, here in gray, one placed by a machine in blue, and one assembled by a human, here in yellow. And multiple of these Y triplets define the structural logic of the system, a reciprocal space frame. So first, humans interactively designed on the fly, so they decided in which direction the structure should grow. And after picking the first element of the new Y triplet, users initiated the robotic fabrication. And then the robot placed the second element in the Y triplet, and the human placed the third element and closed the Y triplet. After closing the Y triplet, the fourth step was to connect all 3 struts with rope joints. And then, of course, it was manually placed. That means we were testing different tracking systems to then include manually placed objects and actions back into the digital model. We tested it in actually building again everything on site, where we're also designing on site. And the follow-up project, Collaborative Augmented Assembly, can be also seen here at TU Munich, a project together with many great collaborators, Professor Dörfler, Lidia Donasova, Professor Pierluigi D'Aconto, Mashito Ojad, and my students, Eleni Alexis and Joseph Kenny, and just to name a few. And we will show also part of that work as part of the workshops. I want to use the last minutes of my presentation with a project that comes from a different context, but talks about the same questions that I showed in the more, I would say, projects closer to actual construction procedures. It looks at embodied computation, so not just how we can use human input to instruct machines or be instructed during fabrication, but also what does it mean if we continue collaborating, communicating, interacting with machines in the architecture that we are building. It's called Degrees of Life, and it was a responsive environment exhibited at Zentrum Focus Forschung in Vienna, together with my colleagues Tiziano Derme and Barbara Imhoff. And it was part of a longer research project, 4 years, called Co-Corporeality, and it focused on how human presence can manipulate the growth or the actions or reactions of biomaterials. And Degrees of Life was the first full-scale proto-architectural installations, testing the results of the research of Co-Corporeality. Degrees of Life aim to develop an interactive environment within an architectural space that can learn, grow, and decay in relation to the human presence and behavior. So for the nonverbal communication between the human and the living material, I was using an eye-tracking device that was able to detect where a visitor is in space and at what the visitor is looking at. The exhibition was articulated around 3 distinct self-sustaining closed environments, hosting 3 different types of bacteria. Although the enclosed environments provided the necessary environmental conditions for the bacteria to survive, they relied on human interaction and mechanical actuation to thrive. So here you can see these 3 distinct self-sustaining and enclosed environments, hosting 3 types of bacteria: Escherichia coli bacteria, Sucrofermenta, and cyanobacteria. And here was the eye-tracking localization station. And they all relied on human interaction and mechanical actuation to thrive. So here you can see an interaction with the Escherichia coli environment. I tracked the human interaction by using an eye tracking. So I registered in real time by a wearable eye tracking device that recorded humans' local position, but also the pupil gaze direction with 3 different types of cameras. And this setup allowed us to record conscious as well as unconscious data. And I want to highlight that because it was one of the projects where I also tested on what it means to distinguish between conscious and unconscious human data and implement that in machine reaction and the digital environment. And unconscious data we tracked, for instance, was gaze duration, pupil diameter. And this eye tracking was then used to start an interaction routine and visualize the data in real time projected onto the space. And depending on what the environment the human looked at, the exact gaze direction within that environment and the intensity of the gaze, a corresponding machine reaction happened and was activated. So the machine then stimulated, fed, visualized, or directed bacterial growth within this specific spot. So all 3 environments were triggered according to the needs of the hosted bacteria. And here you can see a picture of the E. coli environment, the sucrofermenter environment, and the cyanobacteria environment. And I want to just summarize where I say that all this project shows different means to enable inclusion of human intuition and dexterity in digital processes. By allowing humans to actively interfere in digital fabrication, interact with digital processes, adjust them, and manipulate them intuitively and on the fly. It also shows us the potential of including conscious and unconscious human actions and the technical, aesthetical, and philosophical potentials that could emerge from including humans in digital fabrication. Thank you very much.